Hello, students! Today we're going to tackle a really important topic in organic chemistry, diazonium salts. Now, I know this name can sound a bit intimidating, but trust me, by the end of this session, you'll see that it's one of the most powerful tools a chemist can have. So let's get started. You know, have you ever looked at a brightly colored fabric, or maybe even the ink in your pen, and just wondered, how are these amazing, vibrant colors actually made? Well, the answer lies deep inside the chemistry of aromatic compounds. The secret is a very special, highly reactive molecule. I want you to think of it like a master key. It's a key that can unlock chemical pathways to create a huge variety of aromatic compounds, many of which are really difficult to prepare any other way. And that master key, my friends, is the diazonium salts. These salts are what we call crucial synthetic intermediates. Now, why is this so important for us? Because they allow us to take a simple aromatic amine and transform it into a whole world of other useful compounds, including those brilliant dyes we were just talking about. So, what is a diazonium salt really? Let's break it down. At the simplest level, just think of it as a temporary, activated form of an aromatic amine. It's like we've given the amine group a supercharge, making it ready to react, ready to be swapped out for another group. Okay, so how do we make this highly reactive intermediate? Well, the process has a specific name, and this is very important from an examination point of view. Let's look at how it's done. The process is called diazotization. Now, for your exam, this is the anchor definition you must remember. It's the process of converting an aromatic primary amine into a diazonium salt using nitrous acid at a low temperature. Simple as that. All right, so what do we need for this reaction? What are the key ingredients? First, we need an aromatic primary amine. A classic example is aniline. Second, we need nitrous acid. Now, nitrous acid is a bit unstable, so we prepare it fresh or in situ by mixing sodium nitrite with hydrochloric acid. And third, and this is absolutely critical, the reaction needs to be kept very cold, between 0 and 5 degrees Celsius. And when these three ingredients come together under these cold conditions, the transformation happens. We create our target molecule, the unstable, but as you'll see, incredibly useful intermediate, the diazonium salt. Now, I've used the word unstable a few times, and you might be thinking, isn't instability a bad thing in chemistry? Well, in this case, that instability is the secret to its power. Let's find out why. I want you to hold this one analogy in your mind. A diazonium salt is like a grenade with the pin pulled. It's just stable enough to hang around for a short time, but it is primed and ready for a very powerful reaction. So you see, this instability isn't a weakness. It is the source of its synthetic power. The diazonium group, the N2+, is what we call an excellent leaving group. And why is that? Because when it leaves the molecule, it forms nitrogen gas, N2. And as we all know, nitrogen gas is an extremely stable molecule. The whole reaction is just waiting to happen because it wants to release that super stable nitrogen gas. And this chart here shows exactly why that temperature is so critical. Just look at this. At 0 degrees, the salt is relatively stable. We can work with it. But bring it up to room temperature, around 25 degrees, and it starts to decompose. And if you warm it to 50 degrees, it decomposes rapidly. This is exactly why the reaction must always be carried out in an ice bath. Now, here is a very common point of confusion for students. Why does diazotization work for aromatic amines, but not for aliphatic amines? The answer, in one word, is resonance. In aromatic diazonium salt, that positive charge on the nitrogen is shared and spread out over the benzene ring. This resonance effect stabilizes the ion, making it just stable enough to be useful. Aliphatic diazonium salts, they have no resonance stabilization, and so they fall apart almost instantaneously. So, now that we have our grenade with the pin pulled, what can we actually do with it? Well, this is where diazonium salts become a chemist's secret weapon. They open up a whole universe of reactions. Let's look at this reaction toolkit. This table summarizes the most important ones, and I want you to notice the pattern here. In almost all these reactions, the N2+ group is simply replaced by something else. For example, in the Sandmeyer reaction, we can use copper salts to replace it with a chloro or a cyano group. If we just warm the salt with water, a hydrolysis reaction happens, and we replace the N2+ with an OH group to make a phenol. And finally, the most famous one, the coupling reaction, where it reacts with another aromatic compound like phenol. And this coupling reaction, well, this brings us right back to our first question. Its most famous application is creating those amazing, vibrant colors we see all around us in dyes and pigments. And this isn't just some textbook chemistry, it is hugely important in industry. As you can see from this chart, making azo dyes is a massive application. But it's also fundamental in making pharmaceuticals and for preparing all sorts of other aromatic intermediates, which are the building blocks for even more complex molecules. Okay, we've covered a lot of ground today. We've gone from a simple amine to this incredibly versatile intermediate that can become almost anything. So let's quickly recap the key takeaways that you need for your exams. Here is your final revision checklist. Just 3 points. First, the core idea. Diazonium salts are unstable, reactive intermediates made from aromatic primary amines. Second, the mental picture. Remember that grenade analogy. They're super reactive because N2+ is a fantastic leaving group. And third, the key example. They're essential for making colorful azo dyes through coupling reactions. So what's the final takeaway? Look, if you can just remember the core idea, that mental picture of the grenade, and the key example of azo dyes, I promise you this topic will feel so much lighter and easier for you in your exam. Keep practicing these reactions, and you will definitely master this topic. All the very best.